So anyway, actually, I thank you, Ashish Upadhyay, and all the members of the trust for giving me this opportunity. So Ashish has given a very comprehensive uh, account of topology and geometry of three manifolds. My purpose is different. I am not actually uh, not going into the complete details of those results, but my purpose is the following. See, I have read an article by Robert Meyerhoff in Mathematical Intelligence several years ago. It was in 1992, and I was delighted to read it. I presented some of these materials in an earlier conference at Allahabad in 2000 and 2001. It was at SRI. Yet again, after 22 years later, I still feel like sharing my delight of reading that paper with at least the uninitiated participants. Needless to say, I do not claim any originality in this article and strongly recommend the reader to go through the above cited paper to get a fuller picture. It will introduce the reader with nature of hyperbolic metric in 2 and 3 dimensions and also discuss 3 invariants defined for the hyperbolic 3 manifolds, which have contributed to a large extent to the understanding of these manifolds. So that is my purpose actually. So the first thing is the understanding a manifold involves the following two things. First is that classifying them, that is producing a list with no repetition of all manifolds. And recognizing them, that is developing a usable means of determining where a given manifold fits in the list. The recognition problem is subtle. The manifolds may be given in any form. For example, suppose M is the pair of complex numbers such that x cube plus y cube is equal to 1. So this represents a torus minus 3 points. Actually, x, y, and c means this is a real numbers, x, y are real coordinates. Whereas if you take n and it is given by complex projective plane with homogeneous coordinates x, y, z, such that x3 plus y3 is z3, this represents a torus. Now, thus the recognition scheme should be able to, so therefore what we say that if you are given a manifold in a very bizarre form, like in a equation and things like that, locus of some equations, then it is difficult to recognize them unless you analyze it nicely. Thus, the recognition scheme should be able to deal with all sorts of description of manifolds. We shall be talking about manifolds of dimension 2 and 3. To motivate what it means, let us recall in particular that all closed orientable 3 manifolds, for example surfaces, can be classified, listed as 2 sphere torus, 2 hole torus, n hole torus, etc. So this is we assume this result, okay? That orientable closed 3 manifolds are either this or this or this or this, where n may vary to infinity. 2 manifolds appear to be easy to recognize. Look at it and count the holes. Now, there are 2 difficulties in the above statement. Firstly, looking and counting are not intrinsic to the manifolds. We have to leave the manifold to have a look. For example, when we talk of a 2-dimensional manifold, we are actually talking in terms of its embedding in 3 dimensions. That means we are looking at the 2-dimensional manifold from the perspective of 3 dimensions. So that's why we can identify and make a torus or 2 hole torus and see it from a 3rd dimension, isn't it? So it is not intrinsic. Secondly, so therefore looking and counting is not intrinsic to the manifold. We have to leave the manifold to have a look. Secondly, the manifold may not be presented in a nice way as above, as we have seen earlier examples. So we should try to consider manifolds from the intrinsic point of view, that is remaining within the world of the same dimension. So that means we are living in three-dimensional manifolds and we have to classify three-dimensional manifolds. So we cannot go out of the three dimensions, go to the fourth dimension or fifth dimension and then look at our world and so on and so forth. We have to remain in the three-dimensional world and recognize or the three-dimensional objects inside this world. So for example, this is a two-dimensional object, okay, a two-dimensional plane, and this fellow is a two-dimensional creature. He doesn't know what is three dimensions. So he is exclusively inside two dimensions. And this fellow is standing on two dimensions, but his head is outside the two dimensions. It is in third dimension. So intrinsic means how this fellow looks at the two-dimensional manifolds. That is important. And this is not intrinsic. This is extrinsic. Okay. In the combinatorial approach by Massey to classify two-dimensional manifolds using canonical forms, one starts with a two and gone and pairwise identifies the edges in a suitable manner to get, in particular, a closed orientable two manifold. That is Massey's book contains these details. So like this, if you start with a rectangular sheet and identify this with this and this and this, you get a torus. And if you take an octagon, you identify along these arrows, etc., to get a two-hole torus. But these are not elements of two dimensions. These are outside the two dimensions, three-dimensional objects. Okay. So the figures before identification are superior to the ones obtained after identification, because the former are intrinsic descriptions of a two manifold. For example, this one is lying in two dimensions, this sheet. So if you just describe this as the torus, that is intrinsic description. Similarly, this one is sitting inside a plane. So if you describe a double torus as this, that is more intrinsic rather than these two. These are not intrinsic objects. So the figures before identifications are superior to the ones obtained after identification, because the former are intrinsic description of a two manifold. All points in the identification space indeed look like R2. See in the figure below the neighborhoods of the interior points, edge points, and the vertices, which are which on identity gives disk neighborhoods up to homogeneity. Okay, so when you identify interior points, will not get identified, so they will look like this. Edge points will have two disks. After identification, they will become one disk, and this four angles, these four vertices will identify it, and they will give a disk. However, in this diagram, these angles will not add up to a disk, but it may increase a little bit, because these angles are 108. So they will, when you count them together, they will not be 2 pi but more. So given a combinatorial description of a two manifold, we want to recognize it. We should be able to do it without extrinsic operation like gluing. Euler characteristics in such a situation gives us the desired result. For example, if you take 8 gon and look at the Euler characteristic, it will be b minus e plus f is equal to 1 minus 9 plus 6 into minus 2, which is a two-hole torus. So we have emphasized the intrinsic viewpoint because our purpose is to study three manifold and we live in three-dimensional world, unlike the situation in which we try to look at two manifolds by taking advantage of the third dimension. So we have just given one invariant for recognition of two manifolds, namely the Euler characteristic. In dimension 2, there are up to homogeneity constant only 3 geometries. So all these things Ashish has already given in details, but I'm just mentioning for completeness. Spherical, Euclidean, and hyperbolic geometries. Standard models of two sphere, Euclidean plane, and hyperbolic plane. which two manifold admit a geometric structure, that is when it possesses a metric locally isometric to one of the standard models. So the example one, a two sphere admits a spherical structure, take the identity map. A torus admits a Euclidean structure, take the unit square in the Euclidean plane and identify opposite edges via a translation of length 1. It is an intrinsic process. See, I am not folding the sheet to make a torus. I'm just translating the one edge to the another edge by a length 1. Okay. So take unit square in the Euclidean plane and identify opposite edges via a translation of length 1. So it is an intrinsic process. Under this identification, the neighborhood of each point can be taken to be a flat disk. For interior points, there is no problem. For edge points, the two semi-disks get identified under the translation of length 1 along the diameter to give a full flat disk. For the vertices, 4 quarter disks get identified to complete a disk, as the angle at the vertex after identification adds up to 2 pi. See the previous figures. So this one, see these 4 will add up to 2 pi. So note however that gluing the square in 3-dimensional space destroys the metric. See, for example, if you identify like this, the metric is destroyed. So therefore, our identification has to be intrinsic. Okay. Now, the two-hole torus is a hyperbolic two manifold that is admits a hyperbolic structure. To explain this example, we have to quickly recall hyperbolic plane. Now we will take Poincaré disk model. We will not take the half plane model, but Poincaré disk model. The Poincaré disk is simply an open disk in Euclidean plane together with a modified version of the standard Euclidean metric. Specifically, the infinitesimal hyperbolic metric is given like this. For those who are not familiar with this way of putting the metric, I just will quickly go to the appendix and explain how it comes, okay? And then I will come back to this, fine? So let me just go to the appendix. So this one, suppose in the we will mention the convention of representing a metric, okay? So suppose you take a Riemannian or a hyperbolic metric. A metric n manifold is a differentiable n manifold with a smooth choice of bilinear form on each tangent space. Here by a smooth choice, we mean that whenever x and y are two vector fields on M, and look at this is a function, x, that is, these are actually, if you take two vectors, it is a number, but if you take two vector fields, this one is a function. So take this function, this is a smooth function on M. Given by, how do you define this function? X which y of p is equal to xp by p, because xp and yp are vectors, so this is a real number. So this, the definition of this function is defined as follows: value of this at a point is this one for all p in the M. So we call this a metric on M. Recall that tangent space, a tangent vector can be considered as a function which associates to each smooth real valued function f defined in a neighborhood of p a real number xp of f. So it can be thought of as a operator operating on smooth functions on open neighborhoods of M. So xp of f, it is a R. So this is an operator operating on f gives an R. And this has the following properties: linearity, that is xp of a plus bg is equal to a of xpf plus b of xpg, and xp of f into g is equal to xp of f gp plus, that is Leibniz rule is given, product rule. So this is treated as operators. So if tangent vectors can be treated as operators with these properties. Now if x1, x2, xn is a system of local coordinates at a point P of M, the operators del by del xi at P are tangent vectors at P, and these form a basis of the tangent space TP M. If we denote by delta I del by del xi. So these are vector fields, vectorables in a given coordinate neighborhood, whose definition is delta ip is equal to del by del xi at p, these type of vectors. So if x is a vector field in this coordinate neighborhood of p, one can write x as x of xi del by del xi, or in this notation xi del xi. Okay, xi is xxi, and this is, and the value of this vector field is nothing but xp of xi del by del xi, because xp is a operator, operates on this coordinate function, so it is a real number, and this is a tangent vector. Note that this xp of xi belongs to R, and x of xi is a real valued function. X is a smooth vector field if each of these functions xi's are smooth functions. Okay, so this is the notation. We now consider curves in a metric manifold. Now for a smooth or piecewise smooth curve gamma in M from 0, 1 to M, whose initial point is P, we define the tangent vector of M along gamma at P to be d gamma by dt at t is equal to 0. And this is nothing but d gamma of d by dt, where d gamma is the differential. Suppose gamma is a map from here to here. So d gamma is a differential from the tangent space of this to tangent space of this. And this differential evaluates at t by dt, gives you dxi composite gamma dt evaluated at t is equal to 0 del by del xi. So if you write gij to be del by del xi del by del xj, these are vector fields, and gij is the function like this. So this is then the arc length function can be written as indefinite integral st is equal to 0 to t d gamma by dt, which is nothing but you expand this d gamma d by this one, so it will be dxi of gamma dxj of gamma by dt gixj. So this will be the expanded version of this. Here these quantities are replaced by this. Okay, because this is norm, means inner product of this with this. So when you take inner product of this quantity with this quantity, you will get this kind of thing where gij corresponds to these things. Okay, and therefore if you take derivative of this, of the indefinite integral, you get the integrand, isn't it? So ds by dt square, which is this one, is into this one. So in terms of differentials, you can write it as ds square is equal to gij dx0 gamma dxj gamma, which is equal to dx gij dxi dxj. So this is the, so essentially gij is the inner product, isn't it? Gij gives you the inner product, and here we are representing ds square is equal to gij. So essentially this is represented by gij. So when the curve is implicit here. So in Riemannian or hyperbolic geometry, it is customary to refer to the expression ds square above as the Riemannian or hyperbolic metric on M, and ds as the length of the element of the length. So therefore, when I call a metric as ds square or dx square, etc., it is nothing but this quantity. So only the metrics will change. For Euclidean metric, gij will look something. For hyperbolic metric, gij will look something, and so on. Okay, so that is what the notation means. So I come back to the point where I started. Yeah. So therefore, this is the metric, hyperbolic metric, and we define it as in the Poincaré disk model. So it is dx square plus dy square by this one. So gij will be g11 and g122 only, and this will be 1 over this, both cases. So that is the your infinitesimal hyperbolic metric on the Poincaré disk model. Now, when we are near the center 0, 0 of the Poincaré disk, we note that the Euclidean length of the short line segment is the same as that of hyperbolic length. The Euclidean length, hyperbolic length are similar because this quantity becomes very small. So it will become essentially this. So short line segment, same hyperbolic and Euclidean length will coincide. As we near the boundary of the disk, the infinitesimal hyperbolic metric blows up so that the short Euclidean line segment can become very long in the hyperbolic sense. For example, if you take xy very large, approaching x plus approaching 1, then this one is the equal to 0, so this becomes infinite actually. So now geodesics in this hyperbolic plane are the hyperbolic line segment between 2 points measured hyperbolically. Now let us look at some examples. Geodesic segment from 0 to 0p is this is the straight line segment from 0 to 0p. Its hyperbolic length being this one. Now this length comes by using the arc length formula that I have given, d gamma by ds by dt is equal to norm of d gamma, etc. So the norm, in place of norm, you use the hyperbolic metric, okay, and then they integrate. So it will turn out that integration will become like this. The length of this line from 0 to 0p, when we use the arc length function, integral of d gamma by dt norm. So then, if we evaluate with this particular metric, it turns out to be the value of the integral to be this one. Okay, so this is the length of hyperbolic length of a line segment from 0 to 0p. So surely when p tends to 1, r tends to infinity, because this will tend to 0. So it is this. So this is a geodesic line inside hyperbolic plane. I mean, Poincaré model. Now, suppose you take a point geodesic from 0 to p cos theta, p sin theta, any arbitrary point on the disk. And now, what we note before we look at this geodesic and the length of this geodesic, we note one thing, that this hyperbolic metric DSH is unaffected by rotation. So the geodesic from 0 to p cos theta, p sin theta can be calculated by 1, because you just rotate it to a point on the y-axis. So it will look like 0p again, or 0q, something like that. And you can use the first formula to calculate the length. It is again the straight line segment from 0 to this point, at this point, okay. So to calculate the length, you can just rotate it to this point and then calculate using the formula, that log formula, 1/2 log 1 plus p over 1 minus p. Now the geodesic segment between two arbitrary points. Suppose x1, y1 and x2, y2 are two arbitrary points of the Poincaré disk. Then the geodesic segment between these 2 points can be found out using the following facts. First, you note this DSH, that is the metric, hyperbolic metric, is preserved under Mobius transformation of the plane, which sends unit disk to itself. If you take this Mobius transformation, which sends unit disk to itself, then this metric is preserved. That is one fact you have to use. Second fact to use, that one can find such a Mobius transformation which takes x1, y1 to 0, 0. So we can always find a Mobius transformation which takes one of the points to 0, 0. Then we are reduced to case 2, because if out of these 2 points, one of the points is sent to by a Mobius transformation to 0, 0, so it will be a line segment from 0, 0 to x2, y2. So again, you are reduced to the second case. Now the point is, the Mobius transformations are conformal, namely they preserve angle and the orientation. So geodesic from 0, 0 make right angle with the boundary. Suppose you take a geodesic from 0, 0, so they are straight lines actually. 0, 0 to any point, just take straight line, and they fall perpendicular on the boundary. So geodesic from 0, 0 make right angles with the boundary of the unit disk. Note that boundary is not part of the Poincaré disk, because Poincaré disk is open disk. But just to illustrate that it falls perpendicular to the boundary. And so does any geodesic from anywhere in the Poincaré disk, because what we have seen just now is that any geodesic from x1, y1 to x2, y2 by Mobius transformation can be converted into a geodesic from 0, 0 to. So therefore, the angle which this geodesic makes with the boundary has to be, because the angles and are preserved under Mobius transformation, the angle will still remain perpendicular. So therefore, all geodesics will look like this. Those which passes through center will be like this, and those which are not passing through center, they fall on this boundary, because if you transform this to this, then either you transform this to this, so again it must fall perpendicular. If you transform this to this, then again it will fall. So therefore they will fall on perpendicularly on the boundary of the Poincaré disk model. All the above curves drawn inside the Poincaré disk are geodesic, which are parallel to each other. Thus, the hyperbolic parallel postulate is satisfied. That is, given a line and a point not on the line, there exists more than one line parallel to the original line through the point. So, the Euclidean parallel postulate that if you take a point and a line, line and a point outside, then you can have a parallel line, but they will never intersect. But in this case, they will intersect. We now come back to the example of two-hole torus. That two-hole torus admits a hyperbolic structure. The identification of pairs of sides of the Euclidean octagon cannot be done intrinsically in Euclidean two plane, as the vertex angles add up to much more than 2 pi. Because if you keep that picture I have drawn earlier, yeah, this. If you add up these angles, na, they will be much more than 2 pi. So you will not be able to intrinsically identify in two-dimensional two plane. So, however, the identification can be carried out hyperbolically as explained below. So, consider the hyperbolic circle of hyperbolic radius r centered at 0, 0 in the Poincaré disk model. It is a Euclidean circle as well. Take 8 evenly spaced points on the circle and connect them in series by 8 geodesic segments. We have to check the identification only at the vertex, because interior edge points create no problem. That is, when you identify two edges, the interior points and edge points will not create problem, because they will be either full disk or semi disk. The vertex, at vertex we need to have angle sum 2 pi, only then it will fit in a two plane. Because we have 8 equal angles contributing, we need each angle to be 2 pi by 8, that is pi by 4 radians. When r tends to 1, angles tend to 0. And as r tends to 0, the angles tends nearly to the angle of Euclidean octagon, 3 pi by 4. So by continuity, there is a radius. So therefore, when r tends to 0, the angles become 0 in hyperbolic sense, that is, it is in the Poincaré model. And when r tends to 0, angles become large, because like Euclidean angles. So by continuity on r, there is a radius r somewhere in between that has octagon angle pi by 4 radians. This octagon together with hyperbolic identification yields a hyperbolic two-hole torus. So look at this figure. So this is the Poincaré disk model, and we keep on drawing circles, concentric circles, and 8 points on these concentric circles. Now, if you take the r is tending to 1, that is on the boundary of the Poincaré disk, the angles, because they are, this one is also perpendicular, this one is also perpendicular, so this angle is 0. And if you take r very small, then it will be just like a Euclidean octagon, and its angle is 135. So this will add up to much more than 2 pi. But by continuity, if you tend r from 0 to 1, in between there is something like this, whose interior angles will be 45 degrees, that is pi by 4. And this will allow you to identify all the vertices, 8 vertices, to form a planar disk. So this is the thing, okay? So I have written that octagons formed by joining 8 equidistant points varying distance, center 0, 0 inside Poincaré disk model. The vertex angle approaching 0 in the largest circle, and the radii of the circles reduces continuously. The vertex angle increases continuously. One of the smaller octagons become almost like equivalent rectangle with vertex 3 pi by 4 radians. In between, there is a hyperbolic octagon whose vertex is. So I think this picture is much more clear than the words I have spoken. So that is how one do intrinsic identification of this hyperbolic octagon to get a two-hole torus. By using similar procedures to adopt as adopted for two-dimensional manifolds, following results were obtained by mathematicians. So these are old results. So theorem by Moyes, all three manifolds can be constructed by gluing tetrahedra. So when you glue, of course, this is three dimensional, so you are allowed to have a spherical solid angle at vertices. And all closed orientable three manifolds can be obtained by performing dense surgery on links in the three sphere. Ashish has perhaps talked about this one. I will also just give some pictures to demonstrate this. And all three manifolds can be constructed by Himadri. So this was by Moyes, which constructed three manifolds by gluing tetrahedra. Licorice and Wallace has constructed closed orientable three manifolds by performing dense surgery on links in sphere. And this is, of course, a standard fact that all three manifolds can be constructed by Higard gluing. Higard gluing means you take two handle bodies and join them along their common boundaries. So this is. So here, just I give a illustration of the dense surgery. So suppose this is a three manifold and this is a embedded knot inside this. So drilling means you draw a tunnel along this knot. So you drill a tunnel along this knot. And then you fit a solid torus in a suitable manner into this. So that will be the result of dense surgery. So the result of dense surgery is denoted by m minus k gamma. And if gamma is a curve, is homologous. Homologous means H1, if you look at the H1 of the manifold, first homology group. So if it is homologous to P times M and Q times L, where M stands for meridian curve, that meridian curve means curve like this, and longitudinal L is longitudinal curve, this curve like this. So if you take M and L to be meridian and longitudinal curves, then any curve on a surface of the torus can always be written as homologous to Pm plus Ql for some PQ, and which are lying on the boundary of the torus. Then this notation can be also written as m minus k of PQ, where PQ stands for this PQ. Okay, so this notation is used in dense surgery. So now, how this process of filling is done, I just quote something from Ralston's book. So the Poincaré homology three sphere S3 minus K of 2, 3 is obtained from standard three sphere by performing dense surgery along trefoil knot. And if you look at S3 minus K 1, 0, it is the standard sphere because you don't do anything. You simply take it out and put it back. So don't do any modification of the tunnel. So therefore, this is just a sphere itself. So this one I illustrate by Ralston's thing. So look at this. Suppose you have dense construction of homology sphere. Let N be a tubular neighborhood of the right-handed trefoil knot. Suppose K is the knot and this is a tubular neighborhood. N is the tubular neighborhood of that knot. So what I am saying is drilling. So you just take a knot, you drill out the knot, and so you get a hollow tunnel inside this. Let's J curve on the boundary of the knot, boundary of the neighborhood. So J is this dark circle, okay? Dark circle is J. So it runs like this. So two times wrapping in one side, 3 times wrapping in the other side. That's why 2, 3. This 2, 3. And now consider the homeomorphism H from the solid, this solid cylinder, from the solid boundary of the solid cylinder to the boundary of the this tubular neighborhood. And how do you do it? You send the meridian circle 0 cross S1, that is in this picture, meridian circle is something like this. So this one is S1 cross D2. So take the meridian circle this. So that is I'm representing by this. So send the meridian circle to this curve J. So this gives a homeomorphism. And then you quotient define a space union of this one and this S3 minus N0. N0 means S3 minus N0 means you take the drill out this, whatever is leaving left inside S3, that is S3 minus N0. So take S3 minus N0 and this solid cylinder and attach it along this homeomorphism. So saving a solid torus to the knot exterior via H. Okay. So this manifold is the result of dense surgery. And actually this is the homology 3 sphere. So this is how this identification is done. Okay. So that is illustration. Now we give some more illustrations. So this is from Rolson page. I have given reference also. So if you want to construct a length space PQ, how do you do it? You just take a sphere and then identify this point with this point. That is supposed to rotate like this and take reflection on equator. This. So identify this with this one. So this is how we construct length 3 space. Now the Higard gluing I was talking about. So Higard gluing is the reverse process of Higard splitting. If you split a manifold into two handle bodies, so that is splitting. And if you glue the two handle bodies to form the manifold, then it is Higard gluing. So therefore, this is a solid 3 sphere. So the solid 3 sphere can be written like this. And what you do, you cut it in 5 pieces like this. So I am using this pentagonal shape, 5 pieces. And then what you do, you turn them around, these things turn them, so this becomes outside. And these red things becomes top. So, and then identify, because eventually these red ones are identified. I have just cut them out apart, but we have to eventually identify them back. So this has to be identified with the bottom. So we get a torus like this. So this is a handle body. On the other hand, the interior part, this part is represented like this. Here also you have to identify this with this. So when identify this also torus. So because this is the union of the interior part and outer part gives you this. So therefore interior of these two gives. So this is a Higard splitting of this. And if you start with these two and using this process, glue them, then you get this. So Higard gluing and Higard splitting. So using a specific example of length space, we have demonstrated what is Higard gluing as well. So most of the results, manifolds can be constructed by 3 manifolds by Higard gluing. Okay, now we come to 3-dimensional manifolds with good invariants. How to tell whether 3 manifolds constructed by above procedures are homeomorphic or not? So we have constructed by Higard gluing, dense surgery, and so on and so forth, identifying tetrahedra and so on. 3 methods: Moyes method, Rolson, and this method, Wallace method, and other method. We have constructed 3 manifolds. But how to tell whether 3 manifolds constructed by the above procedures are homeomorphic or not? We need good invariants, which must be computable and informative. It should be able to distinguish 3 manifolds. Let us consider our old friends. Euler characteristic, the fundamental group, the homology and cohomology groups. Euler characteristic, though quite computable, is not informative, as Euler characteristic of a 3 manifold is 0. For 2-dimensional manifolds, Euler characteristic was complete topological invariant. See, for 2 surfaces, it was a complete invariant, but 3 manifold doesn't give enough information because it is 0. Now, fundamental group, of course, it contains a lot of information and is essentially, in fact, Ashish's lecture describes that fundamental nature of fundamental group gives you the nature of the geometries that you have on 3 manifolds. So therefore, it is contains a lot of information and is essentially straightforward to compute. But it cannot be considered as good invariant because information about 3 manifold is hard to extract. The groups are hard to work with. Homology groups are often able to distinguish between 3 manifolds, and they are relatively easy to compute. So they are to some extent good invariants. However, there are broad class of manifolds which they fail to distinguish. For example, all knot complements in 3 sphere have the same homology groups. Further, the homology. So you know that most of the good hyperbolic manifolds obtained from not complements, but homology doesn't distinguish them. Further, the homology groups of this dense surgery of this and this are the same if P and P prime are same. In particular, homology does not distinguish between S3 1Q from 3 sphere. This is a standard 3 sphere, and this is a obtained by density of 1Q. But homology group will not distinguish between these two. So we need good invariants. But topological approach is running out of steam. So we should look for geometric structures. Now, a hyperbolic 3 manifold. A hyperbolic 3 manifold is 3 manifold with metric locally isometric to hyperbolic 3 space. In this case, we also the space hyperbolic 3 space can be described in Poincaré 3 ball model as open ball with the metric this. So this one is similar to the two-dimensional metric we have considered. Only thing that number of coordinates has increased. Now the first example we give is Seifert-Weber dodecahedral space. It is a closed hyperbolic 3 manifold described as follows. Now, one thing Assis has described is that this Poincaré dodecahedral space in which two opposite faces are identified by 1 by 10 of 2 pi, and this 1 by 10 of 2 pi is least that is required. The reason is that if you draw a dodecahedron, then you will notice that one pentagon on the top and one on the bottom, the vertices are not aligned. One of vertex and if you look at the corresponding vertex, then there is an angle. So 1 over 2 pi by 10 angle is there. So therefore, if you have to just straight away identify the vertices and edges, you have to have at least 1 by 10 2 pi. So that is the Poincaré dodecahedral space, and that actually gives a model for and that of course is not a closed manifold. That Poincaré dodecahedral space which Assis was talking about is an open manifold. The boundary is not taken into account, because if you include boundary, again the same problem will come. How to reduce the angles, the dihedral angles to match. So that is open. And of course, it gives a model for homology 3 sphere. So here, we don't take 1 by 10 2 pi, but we clockwise twist 3 times of that. So a Seifert-Weber dodecahedral space is constructed topologically by taking a regular dodecahedron. So dodecahedron contains 12 pentagonal faces, 3 at each vertex, and identifying opposite faces by 3 by 10 2 pi by a clockwise twist. Interior points and faces do not create problems. Edge points needs analysis. Each edge is the manifold comes with 5 identified edges in the dodecahedron. Thus, each dihedral angle means this kind of angle, like this. So this is dihedral angle. So each edge is having 5 identifiable edges in dodecahedron. Thus, each dihedral angle at an edge of the dodecahedron must be 2 pi by 5 radians. Only then they will add up to, because 5 of them have to add up to give 2 pi radians. Then only we'll get this kind of thing. So we use same technique as used in the case of two-hole torus to construct regular hyperbolic dodecahedron in hyperbolic space, having dihedral angles anywhere between 0 and this degree. In particular, the hyperbolic edge condition is satisfied for 2 pi by 5 dodecahedron. So here again, if we look at this dodecahedron, which is very small, the angles, dihedral angles are very large. So if you add 5 of them, it will not be 2 pi. So you keep on reducing, increasing the size, so it increases. When you increase very much, the angles become very small. In between, the angles become 2 pi by 5. So then you identify, as we have done in 2-dimensional space. So like this, if you have taken sufficiently large, after using continuity, sufficiently large radius, then the dihedral angles become 72, and 5 of them will give you 360. So this is the ideal dihedral angles for intrinsic identification of opposite faces as an hyperbolic dodecahedron for constructing a Seifert-Weber dodecahedral space. Now, Thurston work has indicated that a typical three manifold is either topologically simple, that is topological classification exists, like ciphered fiber spaces, or possess hyperbolic structure. All but finite number of three manifolds obtained by performing dense surgery on a given hyperbolic knot, that is knot in S3 having hyperbolic complement. That is neither a torus nor a satellite knot, possess hyperbolic structure. So all but finite number of three manifolds obtained by performing dense surgery has hyperbolic structure. So consequence of this is that, Thurston's work is that hyperbolic three manifolds are the most abundant, the most complicated, and the most important class of three manifolds. So an approach to understand three manifolds topologically is to restrict attention to hyperbolic manifolds and to use the hyperbolic structure to define hyperbolic invariance. So this is a illustration of ciphered fiber space. What happens, you have to identify top and bottom, but you identify this with this with this, and so on. So so this is using 5-2 torus curve 5-2 is obtained by doing the top cylinder, bottom by 2/5 rotation counterclockwise. So by identifying the top and bottom by a twist gives you the fiber cipher space. The following theorem Mostow ensures that these hyperbolic invariants are topological invariants as well. If a closed orientable three manifold possesses a hyperbolic structure, then that structure is unique up to isometry. So if the hyperbolic invariants are this isometry invariant, then they're unique in some sense. So three most natural hyperbolic invariants are the volume, the Chern-Simons invariant, and the eta invariant. I will just touch upon them for completeness. So the volume of a hyperbolic three manifold is defined as follows. In the Poincaré-Paul model, the infinitesimal volume form is given by this. Okay, this is the volume form. The volume of hyperbolic tetrahedron, because by Moyes, a hyperbolic three manifold can be constructed by identifying hyperbolic tetrahedron in suitable manner. So volume of a hyperbolic tetrahedron is computed by integration. Thurston has given a formula for volume of hyperbolic tetrahedron in terms of its dihedral angles in his Princeton notes, which Ashish has referred to. The problem of computing volume of hyperbolic three manifold reduces to problem of decomposing it into hyperbolic tetrahedra. So Jeffrey Weeks has developed a computer program that carries out the decomposition in enormous range of cases. So therefore, since you can calculate the hyperbolic volume of tetrahedra, and every three hyperbolic three manifold can be decomposed into tetrahedra. So by adding the volumes, you can do it, but it is not an easy job. So this computer program was required. Now this is a figure 8 knot. Now the volume is an informative invariant in that it can distinguish between hyperbolic three manifolds which have the same homology. Homology may be same, but their volume may be different. So that will distinguish. For example, K be the figure 8 knot, this one, figure 8 knot. And then let you take the dense surgery, S3 minus K, be the result of dense surgery along K, this figure 8 knot. Then for PQ, not of this form, that is, PQ should not be of this form, this. You exclude all these cases. Then for other cases, this has a hyperbolic structure. There are finitely many cases you have to exclude, and remaining cases, it will be hyperbolic, has a hyperbolic. And it has been calculated that this S3 minus K71, S3 minus K72, S3 minus K73, 74, 75 have all different volumes, though they have the same homology. Thus, the Mostow theorem, they are non-homeomorphic. So they are distinct manifolds. Okay. This is Whitehead link. The volume is, however, not complete invariant. There are non-homeomorphic hyperbolic three manifolds with the same volume. Let K be a complement of the left-handed Whitehead link. Then S3 minus K of 1,1 and S3 minus K 5,1 have the same volume but are homeomorphic. They are not homeomorphic. Their homology groups are different. So therefore, volume also is not a perfect invariant because see these two have same volume, although they are can be distinguished by homology. So therefore, it improves the homology, but it is sometimes weaker than homology. So these are not really complete. Now we come to another invariant, Chern-Simon invariant. Let M be a closed oriented three manifolds. Let Fm to M be the oriented frame bundle. Okay, frame bundle means this elements of these are frames. That is each if you take a point and if you take a fiber, it is a frame of that is a frame means a basis, orthogonal basis or something. So this is a so therefore the elements of these are frames. So Chern-Simon has defined a complicated three form on this frame bundle, and using parallelizability of M, any oriented three manifold is actually parallelizable. So using parallelizability of M, one pulls back the three form via section, because section will exist only when you have a parallelizable. Of course, parallelized mind certainly will have sections. So since M is parallelizable, sections always exist. So you take a section, pull back the three form which you are defining on this. So this, and integrate it along M. So this is a real number, but this number changes with the choice of the section, because you can have many sections, and for each section you have a different real number. But these numbers differ by integral multiple of 1 over 2 pi r, and these integers are the degree of this map F from SO3, and which determines the change of choice of sections. Because if you change the section but to another section, they will differ by a map like this. So this defines the choice of determine the change of choice of section, and look at the degree of this, that is an integer. So the difference between these two frames will be 1 over 8 pi square into that integer. And therefore we define Chern-Simon invariant as a not a real number but a element of the quotient R by Z. Okay, 1 over 8 pi square is a star of Q R by Z. So it is a quotient actually, not a real number. So this is called Chern-Simon invariant. And Chern-Simon invariant is useful as it distinguishes three manifolds with same volume. That is, volume may be same, but they have different Chern-Simon invariant. So it has improved that. But it also has limitation as it is not complete invariant. So now this is the last one. I think I will complete in 1 minute. Let M3 be a closed oriented Riemannian manifold. Consider the operator A on the even forms on M. Even forms will be like this. There are three manifolds. So there are only omega 0, omega 1, omega 2, omega 3. So look at this. So, and these are the Haas star operators, which some kind of duality operator, okay, in differential forms. So look at the this operator A defined like this for B is equal to 1 and 2. The eigenvalues lambda of A are all real and can be either positive or negative. Atiyah, Pataudi, and Singer have defined eta S. S is a complex number to be the sigma lambda not equal to 0. Sine of lambda is this eigenvalues of A. Mod lambda to the power minus S. And this is a function, complex function. It has a meromorphic continuation to the entire complex plane and does not have a pole at 0. Therefore, it follows that eta 0 is well defined because it doesn't have a pole there. So we defined eta invariant to be eta of M is equal to eta 0. So this is eta invariant of a manifold. Now, eta invariant and Chern-Simon invariants are related by the formula. The 3 eta of M is equal to CS of M mod Z, because they are not equal, but they differ by an integer. Eta invariant contains information that Chern-Simon invariant does not have. There are examples of three manifolds with equal Chern-Simon invariant but different eta invariants. But certainly, since I'm not going to details of this, so I just conclude. So Sela is one person who has given isomorphism theorem of groups, hyperbolic groups, and it was extended by another person, reference given here. So what he told Sela was that in geometric topology, one of the main goals is to find effective algorithm in order to generate a list of containing exactly one n manifold for each homeomorphism class. The classification task is related to homeomorphism problem, that is, possibility of provide an effective procedure for determining whether two given n manifolds are homeomorphic. Even though the terms effective and given must be used in a precise way, under reasonable interpretation, it is agreed that two problems are solved for two manifolds and unsolvable for manifolds n minus n greater than or equal to 4. They cannot be solved. These two problems are equivalent to three manifolds by Hampel. A complete solution to the homeomorphism problem is therefore one of the ultimate goals of three-dimensional topology, world Hamilton, and requires much more than what our theory provides. Theory means Sela has given a theory of isomorphism, solution of isomorphism problem, hyperbolic groups of certain specific kind. This fellow, this Dahamani and so on, they have further extended that result. Despite the solution of Thurston's geometrization conjecture, the conjecture which Ashish has stated, I'm repeating it, let M be a closed orientable prime three manifold, then there is a embedding of disjoint union of two Tori and Klein bottle in M such that every component of the complement admits a locally homogeneous Riemannian metric of finite volume. So this has been solved by Perelman, C. Morgan and Milner, etc. The classification of our hyperbolic three manifold is still distant goal. Although Thurston geometrization conjecture is proved, the above invariants, namely volume, Chern-Simon invariant, and eta invariant, are individually or collectively still inadequate to provide complete invariant for the classification of three manifolds. I think I will stop my lecture here. These are the references. So,
thank you, sir. Thank you very much for very stimulating talk. Now, if there are any questions or comments, participants can put forth your questions. Yes, anyone?
Very nicely presented, Himadri ji. Very nice.
thank you.
And sir, what is very noteworthy is that both of you, on a very short time request, I did not want to use short notice actually. So you agreed to give talk, and that actually shows the strength of students of Professor V.L. Sharma ji, as he was always ready to help his students and guide his students. So thank you very much, sir. Okay. I think because there are no questions.
Stop sharing?
Yeah. We can stop sharing and we can close the session by a remark that tomorrow we will start at 9 o'clock as per schedule, and all of us will meet